Today's lesson 5.6 is about linear inequalities in two variables. So we're going to shift focus for just a moment from the systems to introduce the concept of a linear inequality, and then we'll go back to systems tomorrow and you'll see how that all works out. So essentially, we've done a whole unit on inequalities before, and we realized that most of the steps to solving inequalities are the same as equations, with a few exceptions, like flipping the inequality if you divide through by a negative, and graphing our answer when we were done. So in particular, let's talk about the graphing of our solutions. When we did those in chapter 2, our inequalities involved one variable only, and therefore when we graphed it, we really needed only one number line. So we made a little number line, we plotted our point, we decided open or close circle, and we would shade to the right or left. The difference is today we're going to talk about inequalities that involve two variables. So they're going to be linear equations, okay, like y equals mx plus b, or like ax plus by equals c, except we're replacing that equal sign with an inequality symbol. But most importantly, they involve two variables and they're going to be linear in nature. So you'll notice right away that when we go to graph our solutions, we're no longer graphing on a single number line, but we are graphing them on the XY coordinate grid because we'll have two variables. So we'll need two axes to plot our points, okay? So let's go ahead and do some defining here, and then we'll see how we solve and graph these guys. Okay, so a linear inequality, start with that. A linear inequality in x and y can be written as any one of these options, right? These are all in standard form, but we could solve most of these and rewrite them into that slope-intercept, and they might look like y is less than mx plus b, or y is greater than mx plus b, or perhaps y is less than or equal to mx plus b, and you get the idea. Or I guess I'll do it, or y is greater than or equal to mx plus b, right? So if we solved it for y, they would look like this. They're still going to look a lot like our equations. The symbol is what's changed. Instead of an equation symbol, it's an inequality symbol. Okay, in these standard form versions, a and b can be real numbers. It has the same sort of parameters as other linears. And a solution to a linear inequality, so a solution to a linear inequality is an ordered pair that makes the inequality true. Turn on the light here. Hopefully that helps a little bit. Okay, so any point that meets the criteria and makes the inequality true would be considered a solution. Okay, now the graph of a linear inequality the graph of a linear inequality in two variables shows all of the solutions set. So just like with single variable, where we would graph it to show the number line of all the numbers that were available, that's exactly what's going to happen. This is really all about graphing our solutions. When we were doing system of equations, we had the options of substitution and elimination as well. But for these guys, because our solution is an entire region of our graph, we have to solve them by graphing. There really is not another method, okay? The graph is going to give us a visual showing of the entire area. So that graph is going to give us all the solutions to the inequality on the coordinate plane. A linear inequality divides the coordinate plane into two half planes by a boundary line. That's what we're going to be focused on graphing, the boundary line. That's going to be the line made by the equation, where half the region represents the solutions. Okay, and then last but not least, the boundary line is going to be a broken or dashed line if your symbol is a greater than or less than. So equate that to back in the day when we were doing this on a single number line, where you leave it as open circle, right? So it's like the open circle, but for linears, it's going to be a line that essentially looks like this, and it's a broken up line or dashed line, and then it's going to be a solid line for the ones that say less than or equal to. If you see that or equal to bar, that's the equivalent of when we would fill in the circle when we were doing single line, single variable inequality graphing. Okay, so when we do, oh look, it doesn't have a bar, so I'm gonna leave my circle open. Now that's gonna translate to a dashed line. And then when we do the or less than or equal to, it's gonna be a solid line. That would be kind of like filling in the circle. That's, you know, back when we were doing chapter 2. Okay, so let's get started. First of all, we'll start off nice and easy. Let's see how to test a point, because that's an important property of this, is to be able to take in a point and decide if it is a solution. It's also going to be a great way to test your graph to make sure you're shading the right way in just a little bit. So we'll try a couple of these, right? Let's try number 1. So if I want to determine if this ordered pair is a solution to that inequality there, then you guessed it, we'll take this ordered pair which provides an x and y, we'll plug them in and we'll see if it makes it true. Okay, it's got to make the inequality true for that to be a solution. So if we plug in a 3, 2, x is 3, so I'll insert a 3 here for x and a 2 for y, and the question is, does that make this true, right? Is that greater than 5? Okay, well, let's see, 3 plus 2 is 5. Is 5 greater than 5? The answer is no, right? So this fails, and the answer is no. Now, if that had that little or equal to, then actually that would work, but this is a strictly greater than, and 5 is not greater than 5. So that point is not a solution in that inequality, okay? Let's try number 2. If this is the point I am testing, then I'm going to take my linear inequality and I'm going to plug in that x coordinate of 5 and that y coordinate of 3. And I'm going to test to see if it makes this true. Okay, so when I do 5 minus 3, I do get a 2 here. Is 2 less than or equal to 2? Yes, it meets, it's got to be one or the other, and it meets this bottom criteria. So 2 is either less than or equal to 2. The answer is yes, it is equal to 2. So this does work, and that point would be a solution of that linear inequality. Okay, let's try one more on number 3. If you want, pause here, try it by yourself, and then check it. Okay, but I'm going to go ahead and work it out. So here's my x, there's my y. I want to test this ordered pair and see if it's a solution in this inequality. So I'm going to insert this. This is a really good example to do because it reminds you of a few things. Remember to always insert in parentheses. You notice I've been doing that. Really smart thing to do, because that's going to help you keep track of those signs. You have a negative in the equation, or inequality, sorry, and then I'm inserting a -2. Right, so I had a negative that was part of the inequality, and I'm inserting a negative as well. So that's a double negative there. -2 times, and then I'm inserting that -3 for y, and then that all is greater than or equal to 5. If this is a solution, that'll be true. And then let's clean up some of these signs. So the minus a negative or a double negative, that becomes a positive. And then a -2 times a -3, when I do that product, I get a positive 6. And then 2 plus 6 is 8. And then here comes the $1 million question. Is this a true statement? Is 8 greater than or equal to 5? The answer is yes. 8 is greater than 5. It meets that top criteria there. So the answer is yes here, and that ordered pair is a solution. Okay, so that's how you test a point. Plug it in, see if it makes the inequality. Okay, but the reality is at that point is just one of, tremendously many points that could work. Okay, this is one that we tested, but certainly not the only solution to that. In fact, the solution is going to be an entire region, what we call a half plane. Okay, so let's take a look at what that looks like. You have a little step-by-step guide here in case you need a little bit extra guidance, but basically what we're going to do is the following. Okay, the first thing we're going to do is we are going to graph what we call the related line. So I know this is an inequality, and we're going to get to that in just a moment, but right now I'm going to treat this for just a moment like an equation, because that is the boundary line I'm going to draw. Okay, so I'm going to treat this as an equation to find where the boundary line lies. Then I'll come back to the fact that, oh, this is actually an inequality, and then I'll decide where my solutions lie, because it's going to be an entire region of your graph. So let's try number 4. If I take y is less than 2 and change that temporarily for just a moment to an equation, it's the equation y equals 2. Okay, so I'm going to graph this line. So hopefully this rings a bell with our little, hoi vux, little reminder that when I have an equation that's just y equals a number, that's a horizontal line with a slope of 0. So I'm looking at a horizontal line at y equals 2. So that's going to be right here. And this would be my boundary line. So that's going to be where my graph or my grid, my plane is cut in half. Okay, now when I go to make my line, I need to pay attention here because it is an inequality. I'm just using this to find my boundary, but I'm really going to graph this. So when I notice this does not have that or equal to, it's just a strictly less than, I got to remember, oh, that means it's going to be a dashed line, right? So when I go to graph this boundary, I'm going to go ahead and make that a dashed line, and that's the boundary for my plane. Okay, so there is the linear inequality boundary line. Now here's the next question, right? So that's the boundary. I don't want things that are on this line because it's not or equal to, so that's why I left it. It's like an open circle, right? I'm saying, hey, this is kind of the edge, the boundary, but it's not included. What is included is all the y values that are less than this. So think about it. Put your pencil along this line and ask yourself, which half of this coordinate grid would be considered all the y's that are less than 2? Are those y's that are less than 2 above this line or below this line? Right? And hopefully you agree they would be below this line, right? So all the y values that are less than 2 would live down here below this boundary line. And then so we shade that area. Anything in this region makes that inequality true. Sorry. Everything below where that y is 2. So this entire what we call half plane is a solution to that inequality. Any point I pick here would work. Any point I pick up here will not. Okay, and that's the solution. The solution is a region on the graph. Okay, let's try this one right here. You've got 5. Number 5 is x's that are greater than or equal to -1. So for just a moment, I am going to graph the related equation, the x equals -1 line. And again, as soon as I see an x equals for a line, I know it's the special case, the vertical line. So that means I have a vertical line at x equals -1. So it's going to be right there. And then I notice it does have the or equal to. So this does include the boundary, and it's going to be a solid. It's like having that filled-in circle back in the day. Now it's going to look like a solid line. So I'm going to make my solid line right here. That's the linear equation for x is -1. And then now let's go back to this. So that was the related, that tells me where the boundary is, but I really am graphing all the x's that are equal to -1. So I've taken care of the or equal to by making sure this is solid. The greater than part, well, think about it again. If you put your pencil down on this line, would the x values that are greater than this be to the right, or would they be to the left? Well, they would be to the right. I hope you agree, right? So it would be this entire region that contains all of the solutions. You're going to be doing a lot of shading in this second half of the chapter 5, by the way. So yeah, this entire region or half plane would be the solution to that. Okay. All right, flip it over. We'll skip this one. We can do it in class if you'd like. It's another example. All right. Now let's talk about, those were just strictly x and y, but they were linear. So we were still graphing them on a 2-coordinate grid. Okay. Let's talk about things that look like this, right? That looks more like that y equals mx plus b style of equation. And we're still going to graph it like what we just discussed. So for just a moment, I am going to focus on the boundary line itself, would be the y equals 3x plus 1 line. Okay, that would be our boundary line. And again, look at your sign because it does guide you. If I have that or equal to, I can make this a solid line. Okay, So I'm going to graph y equals 3x plus 1, the linear equation, for now, just to make my boundary. So I've got a y-intercept at 1. I've got a slope of 3, so that's a rise of 3 and over 1. And maybe I'll get another point by going back, down, and over. Okay, and back, down, and over. So all of these points live on my boundary line. Okay, and it can be solid because it's got or equal to. So I'm going to go ahead and graph this line as a nice solid line. So that's the boundary to our inequality. And then I need to decide on the shading. Okay, so I want all the y's that are less than or equal to. So I already took care of the or equal to by making this a solid boundary. But I want, again, this cuts our coordinate grid in two halves, right? So I've got this half and I've got that half. One of those contains all my solutions, the other one does not. Okay, so if I want all the y's that are less than this line, right? I want the part that is less than this boundary. Again, I think it helps to put the pencil down and ask yourself, if I were going to go downward, would I move in this direction or would I move in that direction? So think about putting your pencil up against the line and keeping it parallel to it as you move. You know, if I were moving away from this line, this direction would be moving upward, right? This direction would be moving downward. So this is my less than. Okay, you also can see on the y-axis that the y values that are below this are down here, see? So you got your y values down here. So this is the half plane that contains my solutions. Okay, now where to shade can sometimes be tricky for some students. So that is where plucking a point and testing it, like we did on these first few problems, can be really helpful. Okay, so you can say, all right, I'm really thinking it's going to be this half of the coordinate grid, but I'm just not 100% sure. Well, then pick a point that's pretty easy to work with and test it and see if it makes it true, right? One of my favorite points to test, guys, is the origin. Okay, the origin is pretty easy to plug in usually. It's a 0, 0. According to the way that I shaded, the origin should work. It should be in my solution plane. Okay, so I'm going to test that. I'm going to say, okay, if I take this up here and I plug in a 0, sorry, that looked more like a 30. If I plug in a 0 for x and a 0 for y, is that statement true? Well, let's find out, right? 3 times 0 is 0. And then 0 plus 1 is 1. So I get 0 is less than 1. Is that a true statement? Is 0 less than or equal to 1? Yes, it is. And the fact that the point that I picked here, I tested it and it worked, confirms that I shaded the correction. If I had maybe shaded incorrectly or something and I pick a point, you know, let's say I pick this guy right here, negative 1, 0, and I plug that in, you're going to notice it is false. It doesn't work. Like I said, kind of like this guy's, right? So you can always test the point on either side. Whichever side works, that's the region that is your solution. So now I have confirmed with the origin, I've been able to confirm that sure enough, it is this half plane that contains all the solutions. I could spend the rest of the day plugging in other points that are over here and they would all work every single time. Okay, so that's what you tested. Let's do one more. Let's actually skip over to number 9 because that one is in standard form. So you have two options here. Option 1 is leave it in standard and use your intercepts to graph. You know where I lie on this. You can always do that. Or option 2 is to solve it for y. Okay. So if you use the intercepts, there's only one catch. It's less. If you use the intercepts, it's going to be less obvious which half plane you have to shade. So you really are going to have to test a point to decide, should I be shading above or below? Don't trust this guy, because think about what happens when you divide by a negative, right? Sometimes this flips on you, right? So for that reason, even though I like to use intercepts in standard form, I might actually solve this for y to be really sure. So let's solve for y. Let's move the x to the other side. We'll start with that. So now I've got negative 2y is less than, and then I've got a negative x with the 4. So I move the x to the right. And then I still have to get y all the way alone, so I have to divide by a negative 2 And when you divide, you got to do everybody, right? Everybody gets divided. But the most important thing is just a little reminder. With inequalities, anytime you divide through by a negative, you have to flip that sign, right? Remember that? So when we divide by a -2, I get y. And this is now going to be a greater than. And then -1 over -2 is just a positive 1/2. And then 4 divided by a -2 is a -2. So at this point, you should be really comfortable doing that, right? So as promised, the stuff we've done before keeps creeping up. It will all year long, right? So you gotta make sure you're solid on that. So there it is. It's the same equation. Oh, sorry, inequality. I apologize. I gotta retrain myself now. It's the same inequality, but just reorganized so that it is in slope-intercept form. Okay, and then we can graph our boundary line. So for just a moment, we'll graph the y equals 1/2 line. Notice though, I'm going to make it a broken because this is just greater than. So the boundary line, I'm going to want to make it, but it's not going to be included in my solution set. Okay, so I'm going to make it a broken line. But that broken line is going to have a y-intercept of -2 and a slope of 1/2. Up 1 over 2, up 1 over 2, or down 1 and backward 2, down 1 and backward 2. That's where my boundary line lives, okay? And it's going to be a broken line. So let me make that. Some people like to make it and then they go back and erase and make dashes, but I like to make the dashes from the get-go. Okay, so again, there's my boundary. It's like having that open circle. And then it says it wants all the y's that are greater than this boundary. So again, think about it like this. If I put my pencil down and then moved away parallel, which side would be above or greater than this? Would it be going this way or would it be going that way, right? So you can see as you move, this would be kind of the upward motion. That's the half plane that contains the points that are greater. Okay, so there it is. This entire region is the solution to that inequality. Any point at all in this region will work. But if it's right on the line, it will not work. And if it's below it, it will not work, right? It's only this shaded region. And then again, there's that origin. If you think it's a part of the solution, that's a really easy point to test. You can throw that 0, 0 in there and make it 0 is greater than 1/2 times 0 minus 2. 0 is greater than -2, and that is true. Yeah, 0 is greater than -2. Boom. So you know you shaded the correct half plane. Okay? Alrighty. And then we're going to focus on doing the word problem in class. So we're going to skip over that one and finish out with these couple problems down here. This is kind of just the reverse of what we just did. Instead of being given an inequality and us graphing it, we are going to start off with a graph of an inequality solution set, and we're going to write the inequality equation, you know, the actual inequality for it, right? So a couple of tips on this. I like to kind of determine the sign first, and then I just go back and figure out the slope and the y-intercept of our line, and then we're good to go. So if I see this right away, I can see that they shaded not the half plane above, but the half plane below, right? So there's my line. The part that's shaded is the part that kind of falls below this line. So right away, I know this is a less than symbol. I also notice that the line itself is solid, so it must be a less than or equal to symbol. That's the symbol for this inequality. And then I can write y is less than or equal to, and then it's just a matter of filling in the slope and the y-intercept for the rest of this boundary line. Okay, so I'm going to pick a couple points here that are on my line, and I'm going to note that the slope is down 1 over 1, so that's a slope of -1, and the y-intercept was at -2. So you're just working backwards here, and there it is. That's the boundary line, the line that has a y-intercept of -2 and a slope of -1, and the region that's my solution is actually everything that is less than or equal to that line. Okay, let's try one more. Let's try number 12. So on number 12, first, I like to determine the inequality symbol first, personally. So I notice it's a dashed line, and they shaded kind of above it. So again, if I put my pencil up against it and I go toward the shaded region, I realize, oh, I'm kind of moving upward, right? So that's a greater than. I'm above this line. Okay, so that's a greater than symbol. I'm not going to put the bar underneath because it's not equal, right? It's got a dash. So it's strictly, the solution is strictly the values that are greater than this boundary. The boundary line is not included. Okay, so all the y's that are greater than the boundary line. Okay, and then let's just determine the characteristics of the boundary line itself. Looks like it's got a y-intercept at 3 up here. So I'm going to put the little +3 here on the end. That's my y-intercept. And then I'll pick 2 points that are easy to work off of. And I see I have to go down 3 and over 2. So the slope here seems to go down 3 and over 2. So that's my rise over run is down 3 over 2. There's my slope. Okay, so that would be the inequality that is represented by that graph.